Well, thank you for the invitation to be here, and I'm really excited to get the opportunity to talk about a topic area that I think is on a lot of our minds, which is the intersectional space between artificial intelligence and learning health systems, and really how that combination of capabilities and methods is allowing us to digitally transform the way in which we deliver healthcare, and perhaps most importantly, how we make decisions for patients and populations. So, to begin with, I think it is fair to say that it is hard to read a piece of literature in either the general domain or in scientific domains and not see some reference to the AI revolution that is happening at present. And those articles cover a broad range of perspectives. Some are highly optimistic about the potential of AI to reduce friction in human computer systems and improve outcomes, value, and any number of other desirable endpoints. At the other end of the spectrum, there are certainly concerns around the potential for increased bias, inequity, or other problematic outcomes as a result of the way in which we design and use AI. And I use just two examples of many that I could have in terms of how those perspectives are manifest in the health and life sciences. But what I'm going to attempt to do with this talk is really focus on the middle ground, taking a relatively, I hope, reasonable view of both the challenges and the opportunities of using AI in this context. And to that point, if we drill down and talk more about the role of AI in the healthcare IT landscape, it becomes quickly apparent that this is a theme that is dominant. And in fact, it dominates beyond the common examples that we may be familiar with, such as the use of ambient AI in clinical encounters or the use of predictive analytics to drive clinical decision support. Because in fact, AI is really being embedded in almost all aspects of healthcare, from supply chain to workforce management to scheduling to, again, those clinical endpoints that I just talked about. And in many scenarios, the use of AI is somewhat transparent, and we may not even know that modern artificial intelligence tools are being utilized. That is both a challenge and an opportunity when we think about how we study, understand, and optimize the impact of these technologies. Now, for those of you that aren't quite familiar with the idea of how we build and then operationalize AI, this is without a doubt the abridged model of how that works. And by the end of this presentation, you will all be experts in AI. But fundamentally, whether we're looking at analytical or generative AI, we always begin with the principle of collecting, curating, and understanding relevant data that is going to be used to train that model. We then produce a computational model that usually is intended to replicate expert human decision making or some adjacent form of decision making. We then deploy that model, often in the real world for evaluation purposes. We understand its impact, we optimize, we iterate, and then we repeat this process. And the real important takeaways of this diagram is that AI is not static in time, place, or function, but rather is a dynamic technology that requires constant optimization, evaluation, and again, this iterative refinement cycle. Now, back to the idea that AI is a popular theme. This is probably a familiar infographic for many of you from our partners at Gartner, the venerable hype cycle. And in particular, I draw your attention to some of the more recent AI technologies that have been a focus of attention in our field, such as generative AI, which are without a doubt at the top of this peak of inflated expectations. And the real question for all of us is, how will we navigate what comes next, which is the inevitable trough of disillusionment, where many of the promises about these technologies do not come to fruition, and where intense research, innovation, and then application are required to move to the slope of enlightenment and then ideally plateau of productivity. And I would argue, particularly for the research and innovation community, this is the challenge that's in front of us to make sure that we fully realize the potential benefits of generative AI, which are probably not the benefits that we're talking about today, again, because of that peak of inflated expectations. Now, to take a little bit of a deeper dive on that topic of generative AI that I just alluded to a moment ago, this is, again, sort of the simplified version of how generative AI agents are produced. And unlike analytical AI that consume data and predict outcomes or some other decision point, generative AI actually produce new content or new products. we are probably most familiar with generative AI tools like ChatGPT, Gemini, or those provided by Meta that actually produce text or images. But the fundamental idea here is that we again train a model based on some corpora of knowledge. For example, in the case of tools like ChatGPT, the bulk of the public internet and the text and content found therein. We build large language models that allow for us to probabilistically anticipate the right combination of tokens or words that would produce the outcome of interest given some input prompt. And then that yields a general purpose or base model that we can use to predict those outputs that are most likely to answer a question or some other information need posed in the form of a prompt. It is of interest that right now the generative AI tools that we are using in the health and life sciences are actually general purpose tools that are really trained on non-specific content. And we're only just now starting to look at more domain specific tools, as you see in sort of the lower part of this diagram, that may in fact be tuned and optimized for use in healthcare. And a great example might be the use of large language models that are trained on the contents of electronic health records, which largely have not been included in prior training sets. And this may produce more computationally efficient and more domain specific and higher performing models for unique tasks that need that type of knowledge. And again, much like the broader AI field, what you can see here is that we are again navigating a hype cycle for generative AI. And the real question is, how do we move again from sort of those very inflated expectations to tools that truly generate value in terms of knowledge generation and then applied use in the health and life sciences? Now, these are just a few examples. I could have chose many of sort of news that has been present around sort of the relative enthusiasm and the adoption of generative AI and more broadly AI in health and life sciences. And I would point to not only to studies that have shown that most large health systems are now adopting AI strategies, but also that academic health systems are creating dedicated research centers or institutes to help drive a research and innovation agenda around these technologies. And then ultimately, there is a sort of growing interest in the lay public around how will these technologies change the way in which we all interact with the healthcare delivery system. Now, while I won't read this in sort of excruciating detail, I would point out that there are some excellent studies from the National Bureau of Economic Research that provide us with insight into the many different application domains in which these technologies are being developed, applied, and evaluated. And importantly, in many of these studies, there's also a relative assessment of the maturity of these technologies and their potential to generate measurable outcomes or benefit. And if you're familiar with these reports, I think you would agree that these are helpful in navigating that landscape. But if you're not, and you're in a position where you're trying to make a decision about the existence, use, or potential utilities technologies, I really encourage you to take a look at the reports that are referenced in these slides. And I would point out the reports deal with both the use of AI in inpatient and specialty settings, as well as ambulatory or outpatient settings. So really that full spectrum of healthcare delivery environments. But ultimately, and quoting our own friend and colleague Chuck Friedman and his fundamental theorem for biomedical informatics, the use of AI in biomedicine is not really about replacing humans, even though that really is a concern of many people involved, and not without some merit. But rather, it's about augmenting intrinsic human cognitive capabilities in pattern recognition and decision making in light of incomplete or fuzzy information, and making it easier for those individuals to collect, curate, and understand those signals that are most important. And so, per this fundamental theorem, the real goal here is that it is the combination of humans and computers working together that is superior to either working alone. And as that is without a doubt the case when we talk about biomedical AI. And in this same sort of vein, it is important for us to recognize that the ability to achieve that goal is deeply influenced by issues such as the potential for biases in the data that we use to train these models, the limitations of the data or knowledge that we have available, again, for that same purpose. And we also have to constantly recognize that the appearance of intelligence in these tools is not really a function of intrinsic knowledge or critical intelligence of the computational agents, but rather speed and the scope of reasoning. In fact, AI is really about moving faster and at a greater scale than the human brain can in terms of pattern recognition tasks. Now, bringing this back to the concept of the learning health system and maybe framing the opportunity a bit more, I really want to talk about how I believe that AI is a foundational capability that ultimately enables the behaviors that make a learning health system possible. And especially for an audience like this, I don't think I have to go into a lot of detail about this, but learning health systems are environments in which every single time we interact with patients, it's an opportunity for us to learn and improve the care that that individual, their family, or their community receives. And this means we have to instrument the care delivery environment, understand those data, identify meaningful signals, produce new evidence, deliver that knowledge in the right time, place, and format, and then repeat that process. But most critically, this is a set of behaviors, not a physical or built environment. And that means when we use informatics and data science methodologies to support the learning health system, they really need to be aligned with this behavioral lens. So ultimately, as I've already said, the learning health system, if successful, provides this opportunity so that every time we're interacting with human beings, we are in fact using the data and signals that are produced from those interactions to improve the quality, safety, outcomes, value, and benefit of care delivery. And this is my very simplified view of what that looks like when we bring AI to bear on the fundamental behaviors and functions of a learning health system. Because in fact, every time we engage in healthcare operations or research, we produce data and we can use data science and informatics theories and methods to make sense of that data. That produces analytical insights that in turn can be used in the form of contextualized information to inform decision making. We then have to deliver that, as I alluded to earlier, in the right time, place, and format. And then perhaps using a combination of implementation science as well as the fundamental premises of digital health and digital transformation, bring that back into the real world, evaluate, optimize, and repeat this process. And ultimately, what you have here, if you use a biological terminology, is an afferent process of producing signals and acting upon them, and an efferent process in which those actions are realized in the real world. And given just the sheer volume of data and signals that are necessary to realize this vision, AI provides us with the tools to sort through, filter, and understand those thousands, tens of thousands, or hundreds of thousands of data elements that allow humans to function at a high level in this learning health system. And that's really where all these different themes come together. This idea of AI and digital transformation, the adoption of modern computational and data science and communication tools allow for us to finally realize an environment in which those behaviors that constitute the learning health system become practical and realistic to implement at scale in the healthcare delivery system. However, in order to achieve this vision, there really are four critical questions that all of us have to ask every single time we consider the use of AI to drive those behaviors that make up the learning health system. The first is, are the tasks where we are seeking to apply AI even appropriate for the use of AI? And then, if we decide that the tasks are appropriate, do we have the necessary data to train, develop, or validate those AI models? And even if we do have that data, that leads to our third question, which is, what is the evidence standard whereby we judge the performance or utility or desired impact or outcome of AI? And then finally, again, even if we have the right task, data, and evidence standard, how do we really address that final mile problem? How do we bring that knowledge back to the right people in the right time, place, and format? And as I often say to my students, we could have the most elegant and most high functioning algorithm in the world. But if people can't use it, it's still a failure. And that's why question four may, in fact, be more important than any of the preceding questions when we consider sort of this rough template for decision making. And now, what I want to do is really drill down into these key questions. So, first, how do we know if the task that we are trying to tackle in the learning health system using AI is even one where the use of artificial intelligence is appropriate? Now, again, for this audience, I probably don't need to belabor the point, but the fundamental premises of knowledge engineering and sort of affiliated disciplines in informatics is that we need to take raw data, provide context such that it can be applied for a purpose in the form of information, and then build and process actionable knowledge that can be delivered in the right time, place, and format, and create feedback cycles. And there's an example here in this diagram of what that looks like if we take a relatively simple laboratory measure, in this case, blood glucose. But fundamentally, this is based on the idea that we need to be able to act across multiple levels of knowledge generation. conceptual knowledge, which really allows us to understand the basic elements of knowledge and the relationships between them that really comprise a domain. Strategic knowledge, which is how we actually can translate that conceptual understanding of a field into actionable procedures. And then procedural knowledge itself, which is really sort of the rules, algorithms, or activities whereby we actualize knowledge in the right time, place, and format. And this is really, you can think of it as a set of legs on a stool. And if any one of these is weak, then the likelihood that we can build a knowledge-based system, such as an AI agent, is greatly diminished. So, as an example, this is a study that was conducted here at Washington University with our colleagues in critical care medicine and the Institute for Informatics, Data Science, and Biostatistics, where we looked at the criteria that have been proposed in many different peer reviewed publications and large studies for the automated detection of sepsis in inpatients. And I think we all know sepsis is a very important field of investigation due to its high mortality rate for inpatients, and because critical care medicine is often a data rich environment, one in which the use of AI may be quite promising. However, the takeaway from this study was, in fact, that if you take many of the common sepsis risk assessment criteria that have been demonstrated in retrospective studies, mostly using administrative data, and you attempt to calculate them prospectively using the type of data that we find in electronic health record, their performance is extremely poor. And the reason for that is that many of the data points used to calculate these types of metrics do not exist in the EHR during the episode of care. So why am I bringing this up and why did we study this? Because what this means is that we actually don't capture the types of information during standard of care activities that could be used to calculate this type of automated risk assessment, at least as it is currently understood, to identify those patients most at risk of sepsis. This would argue that, in fact, perhaps sepsis risk prediction using these types of rule-based algorithms is not an attainable task using AI because the fundamental nature of clinical workflow precludes the real-time capture of these data elements. Here's another example of a study that we undertook. In this case, looking at sort of emergent adverse events that happen when patients are prescribed opioids along with other medications. And this is really the perennial polypharmacy question. And here, what we found is that there actually are strong signals in our electronic health record that show a correlation between the use of opioids in patients for pain management and other medications that are commonly prescribed for inpatient conditions, whereby we see increased or above average outcomes such as cardiorespiratory arrest, pulmonary embolism, renal failure, or pneumonia. And these are of interest conditions that are not explicitly called out in the data or warnings in the FDA package inserts for these opioids. So in fact, what we're seeing here are a set of signals that will lead us to believe that we have data and patterns in that data within our EHR that may be usable for identifying previously unknown adverse events associated with opioid prescriptions. And this might be valuable from a quality, safety, and outcome of care perspective, and therefore represents an interesting problem domain in which AI might be quite helpful. And then lastly, if we scale to a population level, in this case, you see a study where we actually use geospatial data, socioeconomic data, and clinical data to see if things like area deprivation indices and other indicators of socioeconomic status correlated with access to specialty memory care clinics for patients with neurodegenerative conditions, and in turn, whether the progression or severity of disease symptoms was different between those populations. And in this case, by using that overlay of different data types, we were able to find preliminary patterns that told us that those individuals in areas with higher degrees of area deprivation had lower probabilities of access to specialty memory care clinics, and in turn, the progression of their neurodegenerative disorders was worse than those that did have access to those clinics. And this is an important finding when you think about how access, equity, and other socioeconomic and policy factors influence healthcare outcomes. Again, an example where there are signals in these data that lead us to believe that the data is being captured and is potentially usable, whereby an AI intervention will allow us to surface these types of signals in a proactive way to inform decision making. So now, let's pretend for a minute that we have picked a task. It could be any task of interest, and we believe that it is suitable for the use of AI because we're able to close that knowledge engineering cycle for the development of knowledge-based systems. We believe those data and signals are there, and there is a reasonable intervention strategy. And now we want to know, how do we get down to the real data, the data that is necessary to actually implement that AI development cycle that I showed you earlier? So first and foremost, I want to say that a lot of these projects, particularly in the learning health system, are predicated on the use of data from the electronic health record, or EHR. And this diagram from an article actually that we published a number of years ago illustrates why the use of EHR data in any context, and certainly in this context, is very challenging. So let's say we want to ask a relatively simple question. Did a patient receive a medication in the inpatient setting? There is no singular measure of that outcome or activity of interest. In fact, there are multiple measures that could tell us whether or not a patient received a medication. There could be order entry data, there could be pharmacy data, there could be medication reconciliation data, or administration data, or some combination therein. And we have to make a decision about which one or which combination of these measures we are going to use to decide as a surrogate whether or not a patient received a medication. Because all of these are proxies. None are a direct measure of the administration of the medication to the human being. And so I point this out because depending in many situations how you combine or choose these features, you can get different numerators and denominators. And thereby, you will not always get the same results as your colleagues analyzing the same data sets. And this is one of the big risks imposed by the complexity of EHR-derived data. There are many other complexities which are enumerated here in reference to this article. I'm not going to go into all of them, but I strongly encourage everyone here to think about, as we use EHRs as a living laboratory for the learning health system, are we asking and answering all of these critical questions about EHR data and its fitness for use given any particular analytical task, including the development of AI? Now I'm going to come back to that theme of sepsis that I mentioned earlier. So now what we looked at was more prospective measures that are often used to anticipate mortality risk over time for patients in the hospital. And again, what we found in this instance was that when you take the data that is available in the EHR as it is recorded during an encounter of care and not after the fact in an administrative data context, and we attempt to calculate these many different general purpose mortality risk prediction tools, what we find is that their performance is extremely poor. And their performance is poor because a lot of this data is missing, incomplete, or variable in its granularity. And that speaks to many of the challenges that I talked about earlier surrounding the use of EHR data. So this would be an example of a study that shows that while the problem may be actionable, the current state of the art in terms of the algorithms and the data that we're using to feed those algorithms is not currently fit for that task. In a different way, here's an example of a study that looked at the use of machine learning to predict outcomes for adolescent patients who are going to have scoliosis surgery. This is a notoriously difficult clinical decision because the surgery is complicated, the outcomes are variable, and it's often hard to anticipate the clinical benefit to the patient. Some patients may actually receive better outcomes through physical therapy and other non-interventional measures, but making that choice is extremely hard. And in this case, what we found is that using data in the EHR and conventional machine learning tools in a pilot project, we got extremely promising results in terms of the ability to predict outcomes using a set of measures, as you see in this figure, that are readily available through a variety of sources in the EHR and aligned systems. So this is an example that our preliminary analyses would show us and lead us to believe that there is sufficient data to produce an actionable AI agent that helps with this type of decision making. And again, scaling up to the idea of, well, if I don't have all of that data at my site, but I want to combine data across sites, will that help me with domain coverage or having sufficient data? This is an example of a study that actually looked at sort of the relative comparability of phenotyping algorithms across multiple large academic health systems that were attempting to combine their data for research purposes. And I think we all know that the problem list in the EHR is notoriously ineffective in capturing all the problems patients have because not all are documented for order entry or billing purposes. And so we often use these phenotyping algorithms that use a combination of surrogates like diagnoses, medications, or labs that are adjacent to a primary diagnosis, in this case, type 2 diabetes, so that we can say with more fidelity whether or not someone has type 2 diabetes. And if everybody documented the same way and these data were comparable across sites, these two exemplary Venn diagrams would be identical in terms of their overlap. And they clearly are not. What they demonstrate is that variability in documentation, workflow, and other factors leads to variability in the way in which these phenotyping algorithms would perform using those data from those sites. And therefore, combining data across sites, while promising, is not always a guaranteed solution to sort of data scale and coverage questions. Now, if we have the right task and we have the right data, what about the evidence standards? So this is a great tweet from my friend and colleague Karandeep Singh at UC San Diego, where he said, and I quote, "Research models are rarely implemented and implemented models are rarely researched." And I think this is a very true statement. In fact, when we look at the types of machine learning and other AI models being deployed today in clinical environments, especially those from vendors, there is minimal evidence to show their utility or functionality. In contrast, the burden of getting a model from the lab into production use in the clinical environment is extremely high, which prevents many people from actually getting to that point in the validation of model performance. A great example of that is looking at, sort of back to our favorite theme, the performance of sepsis risk prediction tools. In this case, we see here a relatively highly cited paper that is concerned with the use of a proprietary sepsis early warning system in an EHR that actually showed extremely poor performance. And the reason why that performance was poor was because the model was not adequately optimized or adjusted for variations in populations across different environments. It was an attempt to create a general purpose model. And just to sort of dig into that fact, if you say, okay, let's just do it locally, and that will overcome that problem of sort of finding adequate performance levels, we actually replicated that study across just 9 of the hospitals in our own healthcare delivery system here at WashU and BJC, all using the same EHR and relatively comparable workflows. And in that study, we found that still the comparability and variability in performance was substantial and actually precluded the use of that tool for clinical decision making purposes. Because ultimately, if we're going to build an evidence standard for assessing the performance of AI in the clinical environment, we actually have to ask and answer evaluative questions across all 6 of the pillars that you see on this slide. From understanding the needs of the clinicians or stakeholders that are driving the adoption of the tool, to model development, to local validation, to comparative validation to look at sort of consistency or transportability of outcomes, to model implementation in the EHR and all the technical and functional hurdles that go along with that, to human factors workflow and other studies that allow us to address that last mile problem in terms of how we again deliver this knowledge generated by AI in the right time, place, and format. And the takeaway is this is complex, time and resource intensive, and extremely challenging because there are not always well established gold standards for how to design and conduct studies in each one of these pillars. Now, just to show you an example, here's what happened when we looked at the use of machine learning for predicting outcomes in Alzheimer's patients. And one of the key takeaways is we look at sort of domain coverage of the many different data types that could be used and are known clinically to be predictive of outcomes at a case level basis. What you see is highly variable coverage of those different areas by different predictive algorithm development efforts. And here you can see from this sort of analysis of the literature, the types of data being used at different sites and how they are being employed as factors to drive the performance and evaluation of these Alzheimer's risk prediction models. And actually, you can see not a single sort of one of these data types is used in 100% of the models, even though we know clinically and from a basic science standpoint that these are meaningful features that should be incorporated into our understanding of neurodegenerative disease. And if we take that to sort of the rare genetic disease standpoint, we see something a little bit more promising. In this case, a study that looked at the use of predictive modeling to anticipate outcomes such as optic pathway gliomas or ADHD or plexiform neurofibromas, which are painful nerve sheath tumors in patients with neurofibromatosis type 1. And the takeaway here is that by using a combination of EHR data, demographic features, and additional clinical features that were captured through registries or patient reported outcomes, we were actually able to predict these outcomes with a high degree of performance. And that in turn was justified by a comparison to both expert or subject matter expert driven validation, as well as a comparison to the domain literature and numerous pragmatic or controlled clinical trials that had preceded this study. So in many ways, what this study did was show as sort of a ground truth that we could replicate known knowledge using predictive models in a way that allows us to discover new patterns in this data that could be used to anticipate other, perhaps more complex subphenotypes of NF1. And this is not limited to just the clinical domain, it could also be applied in equal measure to drug discovery. And this is an example using graph theoretic measures in order to understand the interplay between various genes, gene products, and functions in complex biological systems to find out where can we identify druggable targets in those diseases where there are not existing therapeutic modalities. And in particular, are some of those drug targets aligned with existing FDA approved molecules that could be repurposed from studies in other diseases? In effect, trying to use this type of evidence generation and evaluation in a graph theoretic standpoint, validated by biological studies, in order to short circuit the normative drug development life cycle, which is extremely long and costly. And then finally, how do we integrate all this back into the point of care? Many of you are probably familiar with this idea of this trough of despair, but this is about the idea that anytime we introduce a new piece of technology, performance is likely to decrease before it increases, and therefore we need to design studies, support structures, and project plans to anticipate and overcome this barrier to optimal adoption of new technologies, including AI. One of the things that we know is that the ability to explain AI is extremely important. And this is an example of a study that uses relatively simple visualizations to compare the performance of a predictive model to those of known population level indices. In this case, again, this is about sort of looking at various sort of indicators of patient deterioration in an ICU setting and showing real world patient data overlaid with predictive data in an effect to provide a visual explanation to providers, indicating that these data and these predictions are clinically plausible given what we have observed in prior patient populations. And in a similar vein, we've also been working on projects to build self-explaining neural networks. So this is in fact an effort to use machine learning to explain the performance of machine learning. So that we not only extract what features are important, but we can actually show how they are interrelated to one another and how variations in those features actually influence model performance. And again, this is about providing that explanatory facility to clinicians so that they can understand and trust these tools. And by the way, you can again scale these analyses to look at the performance of people interacting with EHRs, especially using novel clinical decision support, such as those that involve AI, and identify where user interface or perhaps user burnout can influence clinical decision making, and how we might want to optimize the delivery of these tools and technologies to overcome burnout and improve the quality and safety of decision making. And this is all a function of actually mining the log files of the EHR to find meaningful patterns, much in the same way that we would do for looking at clinical phenotypes and outcomes in a clinical population. So finally, and just to wrap up, I do want to sort of put this in a broader context, especially with some of the work going on at a socio-technical and policy standpoint. So first, all of the work I described has profound ethical, legal, and social implications. And I haven't spent a lot of time talking about that, but the good news is there's now an effort at the National Academy of Medicine to build what is being called a Healthcare Artificial Intelligence Code of Conduct that actually is intended to bring about a set of standards of behavior for people developing, evaluating, and using AI in the healthcare arena. And this is based on a number of driving or motivating factors, as you see summarized on this slide, which hopefully are not surprising to any of you. You can see here a set of those draft principles. These have subsequently been published in a series of white papers that are available to the National Academy. And you can see this includes everything from human centricity to accountability to transparency to also importantly environmental impact. And I haven't spent a lot of time on that, but the reality is that many of the models we are developing and using now when we apply AI in the learning health system are extremely costly from an environmental, energy, and monetary standpoint. And we do need to consider those factors when deciding whether or not these models are needed and generate useful outcomes that warrant those expenses. I also want to point out that there are a number of convening groups. I'm using one in particular as an example, and this is the Coalition for Health AI that's bringing together groups like our own and many others to share lessons learned, to build practical implementation guides, and to build what are being called assurance laboratories. You can think of them as sort of the underwriter's laboratory for healthcare AI. And if you're more interested in that, I strongly encourage you to visit their website and see how they're helping people to identify tools, to develop tools, to assess performance, and to guide their implementation in a variety of clinical settings. So, to summarize and wrap up, I think if you take a balanced view of an AI-enabled learning health system, on the whole, there is great promise at this intersectional space, as I've described to you, of AI in learning health systems. And that promise will be manifest in many different ways: quality, safety, outcomes, value of care improvement, as well as the health of populations. But If we don't answer the many open questions around how we pick the right data, how we pick the right evidence standard, how we address that final mile problem, there may be significant issues that cause us to not achieve sort of that increased level of performance that we all aspire to with these technologies. And therefore, there is a need for deep partnerships across the community to really answer these types of critical questions. And you can either think of that as a challenge or an opportunity. I think of it as an opportunity for all of us to really lean in and think about how we bring scientific rigor and reproducibility to these fundamental issues. I also want to point out that when you think about this, I encourage you all to consider learning about frameworks from other fields. One of my favorite is this idea of ultra large scale systems, which comes from the software engineering community, which is really about how do we build computational systems to operate in these complex environments like energy infrastructure or air traffic control. And I would argue the health and life sciences are equally complex. And this means we need to be able to design systems, including AI, in the context of the learning health system that are resilient, that can adapt to the needs of many different stakeholders, that are made up of heterogeneous parts that interact, that there is continuous evolution, and that failure will be the norm, and we need to design for that. And I would argue today in the health and life sciences broadly, we ignore many of these lessons learned from other fields, perhaps at our own peril. And then lastly, I'll leave you all with a challenge, which is that I think that achieving this view of building this AI enabled learning health system requires us to move beyond sort of this overly simplified differentiation of basic and applied research, the idea that we do research and then we hand it off to people to apply and learn in the real world. But rather that we embrace this alternative model, which Donald Stokes described based on Louis Pasteur's work as use inspired basic research, where the very same people that are building novel theories and methods are applying them, studying them in the real world, and repeating rapidly. And the entire system in which we operate today is really designed to separate these fields. And I think we really need to think about how do we integrate and bring these views back together. So with that, I'll just say thank you for your time and attention. I provided my email address as well as a QR code where you can download this presentation. And hopefully this has piqued all of your interest to think about how we combine AI and learning health systems in order to achieve that benefit for individuals and populations. Again, where we're using all that data, all those signals, and ultimately the knowledge we can generate to improve the care that we deliver to individuals, their families, and populations. Thank you.